Hey there, physics students. Welcome back to another in the series of rapid review for honors physics. Today the topic is velocity time graphs. And we're going to focus mostly in one dimension. You know that all of motion can be in one dimension or two dimensions or three dimensions. I'll focus on one dimension today. If we look at the number line in this picture here, we see that we could describe motion along this number line as plus and minus, plus being to the right, minus being to the left, and there's this important spot called 0 there, where if we say the position is a positive number, we would then say that the position has plus. So like position right there by the 3, position is plus 3. Or we could have a minus 3 and so on. Displacement, I'll remind you, is moving from one spot to another and comparing where we are compared to where we started out. So if we start out at 3 and we move to 5, the displacement is, let's see, 5 minus 3 equals 2, and I'll put the plus for emphasis there. So displacement, just like position, can be represented with plus and minus. The only difference between the two is that for position, we're talking about where we are compared to the 0 point, and displacement, we're talking about where we are compared to where we started. Okay? Now, velocity is a little more interesting. Velocity plus and minus tells us something completely different. Let's look at the picture here and see what velocity means. Oh, if it's plus, it's moving to the right towards higher numbers. Now, it might be obvious to you that if I'm doing that, or it might feel very natural that velocity is positive there. If I'm moving from position 1 and I'm in the process of moving out and out and out and out, you might think that, sure, my velocity is positive. But it's true even if I'm way over here, like say I started out at -5 and I'm moving to the right, my velocity is positive there. Even though my position is negative, it's possible for my velocity to be positive. So there's no requirement to have velocity and position being the same kind of plus and minus sense. So let's move on then. Let's take a look at how we go from a distance time graph to a speed time graph. Now, by definition, the slope of this graph is speed. It's kind of handy, right? Because we have a distance. Usually there would be meters. I'm going to write that in there because it sort of bothers me that they're not there. Time, t in seconds. Okay, so I have my units. And the slope of this, you'll remember from math class, the slope is rise over run, or change in this case, change in distance over change in time. Remember that the delta means change in. Okay? And if you look at that slope, by definition of slope, change in distance over change in time, we just have distance over time. And distance over time is speed, right? Change in distance over change in time. So what's nice is that from the graph, we can directly get new information. The graph is a distance versus time graph, but the new information we can get out of that is speed. All we have to do is look at the slope. Okay? Let's take another look at another graph. Here, I have a position time graph, and I'm going to try to find the velocity. I have a slight correction to this slide. You'll notice that on the left axis I wrote position, and I want you to think about position, not the word displacement. It's a subtle point, and maybe we can get into that in another conversation, but I think the person who made this slide probably meant to say position and not displacement. So let's see. Here we have position versus time. If we want to find the slope of that, you can see that the slope is change in position over change in time. That is the definition of velocity. We learned that definition recently, right? It has units. Let's see, the change in position and change in time. Change in position would be in meters. Change in time would be in seconds. Oh, good, meters per second. Those are velocity units, which is what we expected to have. Now, we said that plus velocity means moving to the right, and minus velocity means moving to the left. It works out for free. If we use this graph and we do the math correctly, we'll automatically discover which way the object is moving. Take a look at this graph again. You'll see that if we do change in position over change in time for that last segment in the graph, you'll see that the change in position is a negative number. And it's a negative number because we're going from a big position to a smaller position, right? So if you do the math, position final minus position initial, you'll find that it's a negative number, and you automatically get negative velocity from that. Now, I can take that information and convert my entire position time graph into a velocity time graph. Watch this. We go down, we look at the velocity. I see that for the first segment, the velocity is constant, because it's a constant slope. I can do the math. Let me do that in my head. It looks like I changed position +3 over 2 seconds. It looks like my velocity was 1.5. Constant velocity up until some point, and then something happens. Right, now here the graph is flattened out. So when the graph is flat on a position time graph, we know that nothing's happening. So come back to the graph, we see that suddenly there's no velocity, right? Because there's no change in position. And then finally, I'll finish the graph, delta x over delta t. I did this one earlier in my head. It's -2. You can check it out and see if you don't agree. And then we're done with the graph. So that is how you convert a position time graph to a velocity time graph. Let's switch to some practice. I'm going to look at a sample velocity time graph. And for each section, you can look at and answer questions about what's happening. In this velocity time graph, if the object is standing still, that means it's at rest. When is that happening? This is tricky because the answer to that is right here at 9 point something seconds. That's when it's at rest. Otherwise, it's always moving. It's important when you look at your graphs to remember what you're looking at. This is a velocity time graph, so don't be fooled. Just because this section is flat doesn't mean nothing's happening. You're moving at 2 meters per second during that section, so watch out for that. Remember that there's a difference between velocity time graphs and position time graphs. You have to read them differently. Let's come back to this graph and answer a few more questions. When does it reverse its direction? Well, I see velocities positive for most of the time. Look at that, all positive velocities, always moving to the right. I'll say plus is to the right, but here it changes direction. At this point in time, it starts going negative, right? So the velocities are negative numbers. It means it's going the other way. Speeding up and slowing down on a velocity time graph is only asking, how far away are you from zero velocity? So you're trying to look at the magnitude of the velocity. It can get tricky, right? If you look at the graph where the velocity is positive, it kind of makes sense. Like you would look at this segment here and say, yeah, like sure, it's slowing down. What might not be as intuitively obvious, but would be correct to say, is that the object is speeding up on this segment. And it's because the velocity magnitude is getting bigger and bigger. Speed is just the magnitude part of velocity. If you remember one thing, that's a good thing to remember. All right, so let's flip on. Let's go on. I'm going to make a couple comments about speed and velocity and what they mean. You now know average speed, you know instantaneous speed, and you know what they mean. There's a subtle weirdness to dividing a distance by a time, and that gets into calculus concepts, I don't think it's worth worrying about, and I think speed is just what you think it is. It's the reading on your speedometer on your car. Now, velocity, same deal. There's an average velocity that we've defined. There's an instantaneous velocity. I'm going to just say, like, don't worry too much about average velocity. It's not too interesting. It's not too useful. We don't use it very much. But instantaneous velocity is going to come up a lot in this class. So instantaneous velocity, it's change in position over change in time. So you have to change position and change in time. There's a subtle weirdness there. If it doesn't bother you, don't worry about it. If it does bother you, still don't worry about it. And we'll address that in calculus class. Okay? But what you can think about it is the instantaneous slope of a graph. So if you look at this sketch of a graph here, I'm going to draw a little parabola, and I'm going to try to find the slope at some point in time, like right there. All I have to do is take a tangent line. So the slope is the tangent line if you have a curvy graph. At that point, it's easy to get the speed. You can just look at the magnitude of that slope. And if somebody ever asks you, how fast is that thing going? What they're asking you about is speed. Okay? If you have this presentation available in front of you, you'll find there's more practice. I'm going to flip through these very quickly so that you can see them on the video. If you only have access to the video, I suggest that you just pause it and try to answer some of these questions. Okay, we're looking more at the graphs. Comment on this displacement time graph. I faked you out here, right, because it's not a velocity time graph. Be careful when you answer these. Remember that you're looking at a displacement time graph, or you might also call it a position time graph. Be careful. The answers are different than they would be if this were a different graph. More practice here. And I think that's probably all we need to say today. So to wrap it up, we've looked at velocity time graphs, we've understood the meaning of what's in there, and we now know how to read them and analyze them. We'll see you next time.